Okay, so I start right away with what the main point of this paper. So combinations of combinatorial preferences and budgets are very common in practice, but we don't really have any theory for it. The difficulties lay in the fact that whenever we have a budget constraints, the known techniques that we have for the design truthful options are out of the window. And if you're looking for more competitive environments, then we don't have any reasonable market clearing solution. And this paper offers an attractive notion of approximation for market clearing, and we also offer a new bidding language to capture the combinatorial preferences together with the budget. All right, so why is it combination is important? So the obvious example is in spectrum options, right? So you can see that these wireless bands are kind of lumped together in a wide range of bands, and if the two bands are close to each other in the spectrum, then they can likely to interfere with each other. So bidders often have a very complex complementarities and combinatorial preference among this band, and obviously they also have a budget constraint they have in mind. The less obvious example is actually ad options. So this is the common picture that we see in CS talk. But if you're a bidder, here's what you see, right? You have to really tell the auctioneer that what is your budget, right? The answer here is the average that you want to spend each day. If you zoom in, then you cannot really see it well. But yes, for the month, you won't pay more than your daily budget. Some days you might spend less, some days you spend more, but for average of the month, you roughly spend your average budget. And the other thing is that bidders will have to click on the combinations of these keywords. And often the case that keywords also have complementarities property with each other, right? So I want to bundle keywords rather than each individual separately. So there's two features of this picture that I really want you to pay attention to. Number one is that this budget is quite flexible. I don't really have to satisfy this budget as strict. And secondly, if you look at this average monthly searches of these keywords, is range in 100K to 1 million search every day, okay? Or every month. So it's really big kind of options. All right. So what do we do? What do we know when we are thinking about option with budget? So there's two types of truthful option that we can think of. One is the Bayesian compatible incentive compatible mechanism, but it's really work for a single parameters only, and people have tried to incorporate budget constraint to this as well, but it is very limited. The second type, when we have a combinatorial preferences, then we immediately jump to a VCG type of mechanism, but it doesn't really work with budget constraints. Okay, so when market is large, we want to use a competitive equilibrium-based mechanism, but unfortunately here also, we cannot really deal well with budget constraints. So there seems to be a big gap between theory and practice, and the goal of this paper is really want to at least say something, at least in the competitive market regime, that we can offer a new benchmark for options with budget. The reason that we choose competitive equilibrium-based approach is because we are thinking about this kind of a largest options. And honestly, the second reason is that we don't really have any idea that without this large market assumption, how we deal with truthfulness in presence of budget constraint. Okay. So the model is quite simple and standard. So there's single seller. There's an M good denoted by an index J in a capital M set. The available supply for good J is S sub J. And there's N buyers and a set of buyers denoted by a capital N. Each buyers can buy a bundle. A bundle is going to be a subset of a vector 0 and vector. So we can easily extend it to a Z vector with coordinate in Z. But for the simplicities of this talk, just focus on this binary case. And each buyer is going to have evaluations that tell me how much it's worth if you receive that bundle. And we always assume that the empty set 0 vector is its valuation is 0. And furthermore, they have a budget of BI. Okay, so model is simple, standard, and clear, right? So we're going to consider some special case of these valuations, especially additive, assignment valuation, gross substitute, and a little bit more general than that. Okay. So here is the definition of competitive equilibrium with budget. Every agent trying to solve this. Okay? I'm trying to find the best bundle that I can afford with my budget, and I want to maximize my valuation minus the payment they have to pay. Okay, this is standard, and we call it a demand correspondence. If there's a chance that I might be indifference between 2 optimal bundles, so I'm collecting all of them, and I call them a demand correspondence, denoted by D sub I under the price P. Okay. So competitive equilibrium is consists of the price vector P and the demand Xi for each of the agents inside the demand correspondence, such that if I sum up all this Xi together, of course, this has to be less than the supply that I have, and equality is held whenever the price is bigger than 0. Okay? So this is standard market clearing conditions. So why competitive equilibrium is good? Because it's efficient. It's in the core. It's very intuitive, right? You just tell out the price, everyone pick the best bundle and market clear. So it's really kind of very attractive benchmark for people who design auctions. Okay. So again, when we have budget constraints, competitive equilibrium doesn't exist even in the simplest case that agents are unit demand. Okay. So here's the main concept that we are proposing. We say that an alpha beta competitive equilibrium is a competitive equilibrium if we can change slightly the supply vector so that every coordinate we increase or decrease that supply by at most alpha. And for every agent, the budget is either increased or decreased by the beta sum of the highest beta prices. Okay? So essentially, it's that if I'm allowed to change my capacity, my supply by alpha, and the budget of agents, essentially I'm allowing to buy beta more items or less beta items, and I still have a competitive equilibrium that I'm calling an alpha beta competitive equilibrium. Okay? So there's a our goal is really trying to find out for what alpha and beta there exists approximate competitive equilibrium, and we really want to analyze the trade-off between alpha and beta, right? The bigger the alpha is, it means that we have to relax more supply. Bigger the beta is, we have to relax the demand side of the economy. Cool. So here's some of the results. So for additive valuations, we have a 0-1 competitive equilibrium. It means that give me an additive valuations. I don't have to violate any of the supply, but I can relax the budget by the highest price. Yeah. So this is the best possible result we cannot hope for because there's no 0-0 competitive equilibrium in this case. Okay. So assignment valuations is widely used in practice, especially by Milgram's company. He used a lot of this assignment valuations for his auction design. So what is assignment valuations? So imagine here are the set of the items. S is the set of the items, and I have a imaginary set of positions T. And for every subset of the items, I'm defining what's the value of this set. Okay? So the value of this set Z is going to be the value of the maximum matching that I can match Z to T. Okay, so the edges between S and T is captured by this valuations matrix phi. So again, so there's multiple ways that I can really match or assign this set Z to T, but I'm among all the trying to find the best possible ways to match them. Right? So this assignment valuations is actually was proposed back in the early 60s, but Milgram really take advantage of this and really define this class of valuations because it's this very give you the Basel language for expressing a lot of very broad class of valuations. Yeah. All right. So the theorem is saying that for any economy where each agent is an assignment valuations, there's a competitive equilibrium. This is alpha minus 1 beta. Whenever alpha beta are integers, then satisfy this equation. Okay, so it's really you can do the math, and actually you can pull out here this 3 kind of competitive equilibrium. You can have 1,5 competitive equilibrium. It means that I can relax the supply by 1 and the budget by some of the 5 items. Or if I really want, I can do 2, 3, or 4, 2. Yes, so the trade-off here. I either make the supply relaxation small and the budget big, or vice versa. Are you with me? Yeah. Okay. Assignment valuation is a subclass of the so-called substitute preference. Probably everybody in the audience know what it is. Let me just recap it. So what is substitute preference? So here again, I divide the tilde as the demand correspondence of a bidder with no budget. Okay. So this valuation is just Vx minus Px. Okay. So the reason I have theta because the other was have a budget constraint. Now just forget about the budget. Okay. So if the valuations satisfy the fact that if price of one goods go up, the demands of all other goods weekly increases, then we call this class of valuations is substitute. Okay? So it's very general class of substitute. It's more general than the assignment valuations. And until this day, we don't really know how to characterize this class substitutes in a nice way that we can have a compact language to express it. So this is kind of axioms of how the demand correspondence behave. Okay. All right. So for substitute valuations, here's the theorem. Theorem says that if all the agents are substitutes, and I can have this relatively complex formulas comparative equilibrium, and for each of this t value, you can translate into numbers here. So either 1,6 comparative equilibrium or 5,2 equilibrium on the other extreme side. Okay, so I just draw a little picture here. Here's the results for additive. Here's the 3 approximation for the assignment valuation and 4 kind of approximation for the substitute. Okay. 5 minutes left, so I'll quickly talk about can we go beyond substitutes. Okay. And this is kind of new language that we came up with. We call it C assignment. So it's really a generalizations of assignment valuations. So now instead of the goods individually, I'm going to pack them into potatoes, right? Into partitions. And each of the subset inside this partition is going to be potentially mapped to a position. And when it is mapped, it's going to have a valuation value. Okay. So the valuations of a subset is going to be, say, the subset A union B. I'm going to intersect that with the partitions, and I'm going to look at A and B. I'm going to find the maximum matching that I can assign that subset A and subset B to one of these positions in a similar way as the assignment valuations. Yeah. So if each of these subset in the partition is singleton, we get back to the case of assignment. And if we have everything inside only one set, then any valuation can be captured in this way. Okay, so example of this type of valuation, you can think about like spatial options where section of seabeds are up for options and people want options and really want to get locations of this seabed close to each other that can build either drilling oil or building wind turbine. Or even in spectrum options, you can see each of these partitions correspond to the bands that have the spectrum close to each other. Okay, so the results say that if each of these valuation is a 3 assignment valuations, then we have this complex formula, competitive equilibrium. Again, you can see the trade-off between how much capacity we have to relax and how much budget we need to relax. Okay. All right, so the implications of this theorem say that for most of the standard auctions that we can think of, very rich class of valuations, you can actually build in on top of that the budget constraints and submit it as a kind of a sealed auctions and run this approximate competitive equilibrium and get you a relatively good result. Okay. And this is really useful for especially the first picture that I show you, the ad options where budgets are quite flexible and a lot of items, a lot of impressions are for sale. Okay, so how to prove this result? This is quite a fairly complex process, really, but you learn it is quite intuitive as well. So it's really considered kind of 5 basic steps. You first kind of relax this economy and assume each agent now can consume a lotteries of bundles, okay? And really care about the expectations of the budget rather than determining its budget, okay? And once you do that, you're going to express this random demand as a normal demand using an auxiliary quasi-linear utility function. And after that, you can use iterative routing to find a deterministic competitive equilibrium. Welcome you to read the papers to find out. So the conclusions is that, again, we think budget constraint together with combinatorial preference is very common in practice. We don't have a good theory for it. Here we offer you one. And there's several directions for future research. Can we get a better bound? Can we expand this class of utility that we was talking about? And the last one is really, for me, it seems very hard, but if you have ideas, I'm really hope to talk to you. That is how to make this the truthful options. Thank you very much.